Okay, well, welcome everyone. It is very nice to be with you to celebrate Fechner Day, October 22nd, this year, 2020. So it is great to be here. Let's talk about Fechner's contributions 160 years after the publication of the Elements of Psychophysics. Certainly, Gustav Fechner is well known today for his pioneering research in experimental psychology and for his pioneering role in developing essential research techniques that we continue to use today. And so I would like to celebrate Fechner Day with you by demonstrating how Fechner's work has influenced my own research in three completely different areas. First of all, the perception of lifted object weight. Second, aesthetics, right? The science and philosophy of beauty. Fechner studied aesthetics for well over 10 years in the 19th century. And then finally, I would like to talk about visual distance and length perception. And all of these topics were studied thoroughly by Fechner over 150 years ago. So we all know, right, that Fechner helped to create experimental psychology in the 19th century by publishing this book, The Elements of Psychophysics. But I think it's also important to point out that Fechner himself, in the Elements of Psychophysics, believed and said that E.H. Weber, Ernst Weber, in his opinion, really should be called the founder of psychophysics. So in my talk today, I certainly would like to refer to the prior work of not only Fechner, but Weber as well. And so let's begin with that. So Ernst Weber, long before Fechner, published in 1834 a book about the sensitivity of our human sense of touch. And Weber pointed out that we perceive the weight of objects in multiple ways. We can perceive touch in a passive way, for example, by the pressure that objects present on the skin. So if you just lay an object passively on our skin, we do have some ability to estimate and perceive the weight of the object. But in Weber's experiments, he showed that our ability to judge and discriminate weight is much better if we are allowed to pick up and lift the objects with our hands. So I'd like to first look at one of Weber's own experiments from 1834. And you can see from this table that in Weber's book, in this experiment, there were 10 participants. And for my purposes today, I would like to focus only on this second experiment, because it's only in this second experiment that Weber allowed the participants to actively lift the objects. And as Weber said, we perceive and can discriminate weight better once we're allowed to actively lift the objects. The data for these 10 participants in the 1830s is presented right here over in the right. And what Weber is presenting here, right, are the ratios, right, that indicate how much of a difference in weight each participant needs in order, for example, to judge which of two weights is heavier. You can see that for these experiments, the standard weight was relatively heavy at almost a kilogram. But let's take a look, for example, at the first participant. And notice for the first participant needed a difference in weight of 3.2% in order to reliably judge which of two weights was heavier. Notice that there's significant individual variability, right? The second participant, notice, needed an 8.5% difference in weight in order to reliably discriminate which of two weights was heavier. The third participant, right, the difference threshold was 6.7% of the standard. And so if we take the average of the 10 participants, notice that Weber obtained difference thresholds of 6.9% of the standard. So on average, people, human adults, needed a difference in weight of 6.9% in order to reliably determine which of two weights was heavier. In our experiments, certainly we also want to evaluate how well human participants can discriminate object weight, but we also want to evaluate the effects of aging. I mean, after all of us are subject to aging, and I think it's important to know and to determine and scientifically investigate how our perceptual abilities are maintained or change as we become older. So in our experiment, we used Fechner's method of constant stimuli. Our standard weight was lighter than the one that Weber used, 100 grams. We used 6 test weights for each participant, some of which were heavier than the standard by, you can see, for younger adults, 2, 6, or 10%. And we also used test weights that were physically lighter than the standard, again by 2, 6, or 10%. The objects, you can see here's a participant performing the task, and you can see the objects to be picked up and lifted were essentially small cylinders, small plastic bottles. They all had the same size and shape, they only differed in weight. Of course, when the difference in weight is large, then this is an easy task to perform, but if the difference in weight is very small, of course, the task can be quite challenging. So you've seen the test weights, small cylinders. Each participant would pick up one of the objects, lift it a single time and put it down. And so in every trial, the participant would pick up one weight, could be the standard weight, could be a test weight, and then they would pick up a second object, and then the participant's task was a simple one. They had to determine which of the two objects was heavier, the first one or the second one. Because our pilot testing revealed that older adults were likely to be less sensitive to differences in weight, we used a somewhat wider range of test weights for older adults. And as you can see, each participant made a total of 216 judgments or 36 trials for each of these 6 test weights. And you can see, right, a participant performing the task here, and we had 24 participants in this experiment, 12 younger participants. You can see they ranged in age from 18 to 26 years old. And we had 12 older participants, and you can see the mean age was 71 years with a range of 61 to 81 years. Okay, let's take a look at some representative results. In this case, for a single older participant who, notice, was 68 years old at the time. And so, of course, here on the x-axis is plotted these 6 test weights. Remember, 3 test weights are physically heavier than the standard and 3 physically lighter than the standard. right? In each case, they differed from the standard by 3, 9, or 15% for the older adults. And of course, on the y-axis, we're plotting the percentage of test weights that were judged to be heavier than the standard. And first of all, I think it would help to remember what perfect performance would look like. So consider the physically heavier test weights. Since these test weights were physically heavier than the standard, they should always be judged heavier than the standard because they are heavier. So perfect performance for these stimuli would be up here at 100%. Then, in contrast, consider, right, perfect performance for the lighter test weights. Since these test weights are physically lighter than the standard, they should never be judged as heavier, right, because they're not. So perfect performance for these stimuli should be down here at 0, right? They should never be judged as heavier than the standard because they're not. So perfect perceptual performance here, right, would be indicated by a step function. But of course, we human adults are not perfect weight perceiving machines. And so we make mistakes, right? So we make mistakes, but nevertheless, if we make an object heavy enough, we perform very well, although there are some mistakes. And if we make an object light enough relative to the standard, right, we perform well, but still make a few mistakes nevertheless. So we human beings, right, we have good perceptual systems, but they're not perfect. Once we have the 6 data points, which you can see here for, right, performance for the 6 test weights for this older adult, right, we will then find, right, and calculate, right, the smoothest curve that is consistent with the data. And, right, this curve is called a psychometric function. So for each of our participants, we would calculate the best fitting psychometric function like you see here. And then we want to determine each participant's difference thresholds. So to do that is quite straightforward. So we first of all want to determine a difference threshold for the heavier test weights. How much of an increase in weight do we need from the standard in order for the participant to reliably detect the increase in weight? So we go, for example, to the 75% performance, and we then go over to the psychometric function, and we find out that in order for this participant to reliably detect that a heavier object is indeed heavier than the standard, right, you can see that this older adult needed a difference in weight of 9.3%. Likewise, we would like to determine a lower difference threshold. How much lighter would a test weight need to be in order to reliably detect that this test weight was indeed lighter than the standard? And so we go to the 25% point of the psychometric function and then determine the lower difference threshold, which for this participant is 9.2%. So to get a single estimate, then we can simply average these two difference thresholds, and you can see that on average for this participant, this older participant, she needed a difference in weight of approximately 9.2% in order to reliably determine which of two objects was heavier, the first one they picked up or the second. If we look at group averages now, we can see that for younger adults, younger adults needed a difference in weight in our experiment of 6.6% in order to reliably discriminate weight to determine which of the two objects on any given trial was, for example, heavier. Notice that our results are very similar, almost identical to Weber's own results from 1834. So I think that is nice to see, right? That we do the same, essentially the same experiment, nearly 200 years apart, with different participants in different countries and indeed different centuries, and we get the same outcome. But notice, in contrast, that the older adults, on average, needed a much larger difference in weight in order to perform the same task. So our older adults needed, you can see, about 58% more of a difference in weight in order to make a reliable judgment about which of two objects was indeed heavier. Okay, now let's turn to Fechner's results. We've looked at Weber's results. We've looked at our modern results, not only for younger adults, but for older ones. Let's take a quick look at Fechner's own results. So let's return to the elements of psychophysics. And you can see here that Fechner performed this experiment himself in October and November of 1856. Fechner used a variety of standard weights ranging from 300 grams to 3,000 grams. And Fechner used two test weights. He used test weights that differed from the standard by 4%, and he used test weights that differed from the standard by 8%. Let's see the results. So what's impressive to me about this data table, are a number of things, but what we're going to see, these are the results for the 4% difference in weight from the standard, right? When the test weight differed from the standard by 4%. And here are the results Fechner obtained for an 8% difference in weight. And then, of course, we have results for all the way from a 300 gram light standard to a 3,000 gram heavy standard. One thing that certainly catches your attention if you look at this table for a while, notice that so each one of these numbers represents the number of correct judgments out of 512 trials. So notice that just for a 4% difference in weight at the lightest standard, that's already 2,048 trials. So if you then multiply 512 trials for each of these conditions, you find out that Fechner, for this one experiment, made a total of 24,576 judgments. So that is a lot of work for a single participant in a psychophysical experiment. Okay, so let's just look at the results for the 300 gram standard weight. And so to get an estimate of Fechner's performance for the 4% difference in weight at this standard, all we have to do is simply add up these four numbers and then divide by 2048. And then you can see that for this 4% difference in weight, Fechner, on average, was about 66% correct. Now, of course, if we increase the difference in weight to 8%, Fechner's performance should improve. So now we can take these numbers, add them up, divide by 2048, and then you can see that for an 8% difference in weight, that Fechner, right, on average, his judgments were about 73% correct. In order to determine Fechner's difference thresholds, right, we're going to have to interpolate a little. But I calculate that in order for Fechner to perform this task at a threshold level of, let's say, 75% correct, that Fechner would have needed a 9.5% difference in weight. So how does this, notice this performance by Fechner himself compares very favorably to, right, one of my participants who was 68 years old. And notice that Fechner's own results are very different than those of a younger adult. So how old was Fechner in 1856? Well, he was 55, 56 years old. So his own data published in the Elements of Psychophysics indicates, right, the effect of aging that I spoke about earlier. So I think overall, right, our modern results with younger adults agrees very well with Weber's own quantitative results from 1834. And our modern findings with older adults are similar to Fechner's own personal weight discrimination abilities. So one thing that I have always loved about psychophysical methods is that if you do similar experiments in different laboratories and at different times, you usually obtain results that are very similar. So notice our results confirm those of Weber and Fechner, and then we are extending their investigations to, for example, examine the effects of aging. Okay, what about something different? As I mentioned, Fechner studied aesthetics for about 10 years in the 19th century. And remember that aesthetics is the science or that branch of philosophy which is concerned with beauty. And notice that Fechner's book on aesthetics, and there were other books and articles as well, but notice that Fechner's book on aesthetics was published in 1876. So as far as I know, Fechner's research was the first attempt to scientifically study the perception of beauty. So here was an experiment that Fechner performed to begin the study of aesthetics in a scientific manner. His stimuli were rectangles, the same ones that you see here. So Fechner would present participants with 10 rectangles that varied in shape, ranging from a square, right, where the ratio of the sides, of course, is 1:1. And then notice he created rectangles with various elongations, and this one is the most elongated, right? So in this case, the most elongated rectangle, the longer side was 2.5 times longer than the shorter side. So these were his stimuli, and he used something that he called the method of choice. So a participant would look at all of the rectangles, and then they would be asked to indicate which of the rectangles is the most aesthetically pleasing. Very simple stimuli, but an interesting outcome, as you will see. So notice that Fechner had 347 participants, and let's go ahead and look at the results. His results were presented in this table, and for example, you can see here, right, separate rows for each of the 10 stimulus rectangles, and we can see results both for male and female, men and women participants. But I think you would agree it would take a little bit of time to study this table. So I plotted Fechner's results for you so that they're easier, right, to examine the results. So here are the results for the 228 male participants, and we're looking at the results plotted as a pie chart. And notice that the square, right, was apparently not aesthetically pleasing to the vast majority of the participants. Notice very few participants selected the square as being the most aesthetically pleasing. Also notice that the most elongated rectangle also was not aesthetically pleasing. Notice the rectangle that was preferred more than any other in Fechner's study was this one, right? The rectangle where one side was 62% longer than the other, right? So that people apparently preferred the most in a rectangle that had a ratio of 1.618 to 1, which is known as the golden ratio. So apparently, at least the male participants found rectangles that had the shape that corresponds to the golden ratio to be the most aesthetically pleasing. The female participants had the exact same pattern of results. So notice the female participants also did not find the square or most elongated rectangle to be the most aesthetically pleasing. And the females, even more than the males, chose the rectangle, right, whose shape had the golden ratio. Well, I certainly found this experiment to be an interesting one because I think it is a challenge, certainly, to scientifically investigate aesthetics and the perception of beauty. But at the same time, these stimulus shapes are very simple, right? Fechner used and investigated only rectangles. We thought that we would extend Fechner's work and method to objects that have more complicated shapes. And I know it seems unusual, but we decided to use as our experimental stimuli snowflakes. I mean, real snowflakes. So you can see a recent article that we published concerning the visual aesthetics of snowflakes. I think many people would agree that snowflakes are beautiful and certainly have a more complicated shape than rectangles. But notice that snowflakes widely vary in shape, so they make good stimuli for psychophysical experiments. Notice that some snowflakes have a very simple shape so that their shape is essentially a hexagon, whereas obviously other snowflakes have more complicated shapes, for example, perhaps like this one. But I think many of us would agree that snowflakes have interesting shapes. There's a tremendous variety of shapes, and many of them, I think, would appear beautiful. In this context, I thought it was especially interesting to find that scientists have been studying snowflakes and their shapes for more than 350 years. So, for example, we have a book here published in 1665 by a fellow of the Royal Society of London, Robert Hooke. And within his book, for example, he talks about catching falling snowflakes on a piece of black cloth, and that he studied the geometrical shape of every one of those snowflakes. And so here are some drawings of some of the snowflakes that Hooke obtained. And you can see that the snowflakes that he captured or found did vary widely in shape. So this is interesting to me that scientists have been interested in the shapes of snowflakes for more than 350 years. So these were our experimental stimuli, actual photographs of snowflakes. And here's where we obtained our photographs. More than 100 years ago, an American named Wilson Bentley spent decades making photographs, as you can see, of more than 5,000 snowflakes. That would take a lot of time to capture 5,000 snowflakes and take a photograph of each one, right? One by one by one. But Bentley found snowflakes to be beautiful, and he wanted to capture that beauty by taking photographs. So you can see some of Bentley's photographs here. You can see some of the very simple snowflakes that are shaped like a hexagon. And then we can see snowflakes with more interesting and complex shapes. So there's Bentley again. And here is a larger view of one of Bentley's photographs of a snowflake. And I think many of us would consider snowflakes to be attractive and perhaps beautiful in a way that rectangles are not. So those were our stimuli. So for this experiment, we used 50 of Bentley's photographs of snowflakes, and you can see 10 of those that we used here. So here, these are 10 of the 50, but there were 40 more. And we first calculated mathematically the complexity of each snowflake shape, right? So a hexagon has a relatively simple shape, whereas other snowflakes, the shape is more complicated. We wanted to try and mathematically calculate a reasonable measure of the complexity of a snowflake. So what we did or decided to do, right, our measure of snowflake complexity was the perimeter, right? The perimeter of the outer boundary relative to the area, right? So the perimeter of the outer boundary relative to the overall area. And of course, the higher the perimeter, the more complex the snowflake. So we wanted to extend Fechner's research to a more varied and interesting set of shapes. But we, in the first experiment, used Fechner's method of choice. So the experiment is very straightforward. We would present participants with a variety of snowflakes that varied in complexity from very simple to very complex, and ask them to choose which snowflake they felt was the most beautiful or aesthetically pleasing. And here are the results from the first experiment, where we had 204 participants. These are just examples because remember, we had 50 snowflakes, but here are 10 of them to illustrate the complexity. Notice that the simple snowflakes were not preferred. Only 2 participants, for example, chose the most simple snowflakes as being the most beautiful. Notice as the complexity increased that, right, we get higher and higher numbers of participants who choose that snowflake as being the most attractive or most beautiful. So these results in the first experiment certainly seem to indicate the more complex the snowflake, the more likely someone is to choose it as being the most beautiful. In the second experiment, we changed the method a little bit. We had 33 participants in this experiment. And we showed each participant all 50 of the snowflake photographs and asked each participant to estimate the complexity of the shape on a scale from 1 to 10. And then we asked the participant to evaluate or estimate or rate the perceived beauty of each snowflake, also on a scale from 1 to 10. And notice if you plot, right, the perceived beauty of all of the 50 snowflakes as a function of their perceived complexity, notice you get a very linear function. And so once again, it seems to be the case that the more complex the shape of a snowflake appears to be, the more beautiful it will be also. So the conclusion certainly for this experiment are very straightforward. The more complex the shape of the snowflake, the more beautiful it will appear to be, on average. Okay, so let's turn to a third topic. One thing that I do admire about both Weber and Fechner is that they both studied a wide variety of topics, right? They studied vision, they studied the sense of touch, they studied, certainly in Fechner's case, aesthetics. So that makes their work very interesting to me, right? Because they had a broad range of interests. So let's turn to visual length and distance perception. So I'm showing you a page from the English translation of Fechner's Elements of Psychophysics. And we don't know exactly when Fechner performed this experiment about visual discrimination of length, but he says it was performed before December 1856. The experiment is very straightforward. Notice on every trial, he presented two lengths, right? Two visual lengths to look at. One stimulus had a standard length of 2.7 centimeters, and the other stimulus, right, the test stimulus in one condition was 2.5% longer than the standard. And notice that, and so on every trial, he would present to himself two lengths to look at, and sometimes the longer length would be on his left, and sometimes the longer length would be on his right. And he would randomly arrange on every trial whether the longer length was on the right or left. And then you can see that he said he then attempted to judge using vision which of those two lengths was longer, the one on the right or the one on the left. Notice in this case where the test length was 2.5% longer, Fechner said he made a correct decision on every trial. So for a 2.5% difference in length, he was 100% correct, right? But later he says that he reduced the difference in length to only 1.25%. So he made the difference in length smaller between the standard and test stimulus. And then, according to Fechner, when he reduced the difference in length to 1.25%, he says the judgments or his judgments were no longer reliable. So we don't know exactly what Fechner's difference threshold is for parallel visual lengths, but if he is perfect with a length difference of 2.5%, and he is essentially guessing at 1 point with a difference of 1.25%, then certainly his threshold is somewhere in between, and that would, no matter what it is exactly, that's very good perceptual performance, right? So a difference threshold of 1 to 2%, that is excellent, right, performance, in this case for making judgments about length. One thing I found very interesting, though, about his discussion of this experiment is that he could have obtained more exact results, he said, if he had used the method of constant stimuli. So he admits that he could have gotten a better estimate of his difference threshold if he had used the method of constant stimuli, but he felt that that would be too tedious. So in this case, he did not want to make many thousands of judgments. So that's what we did. So in our investigation, since Fechner believed that the method of constant stimuli would be too tedious for him to use, at least in 1856, to investigate the ability to make judgments about differences in length, we decided to do it ourselves. So there were 4 experiments in this study, but I'll just talk about 3 of them briefly. So in experiments 1 and 2, we did use Fechner's method of constant stimuli. Experiment 1 is devoted to investigating the perception of 2-dimensional length. And then experiment 2, right, we will look at visual discrimination of 3-dimensional length. And then later, we'll look briefly at experiment 4, where we use Fechner's method of adjustment. And across these 4 experiments in this study, each participant made a total of more than 7,400 judgments. So it did take a while, but I enjoyed it. So let's consider discriminations of visual length. So here we have 2 line segments that differ in length by 15%. So decide for yourself whether the longer length is on the right or the left. If you pick the one on the left, you are certainly correct, right? So a 15% difference in length is easy to judge. Now here's a 5% difference in length. And once again, it's pretty easy and straightforward. So if you pick the one on the left, you're correct again. So whatever your threshold is for perceiving differences in length, it's probably less than 5%. But now let's reduce the difference in length to 1%. So take a good look, because this is a very small difference. And remember that Fechner himself said that he could not reliably judge a 1.25% difference in length. So if you look at these, if you pick this one, you're wrong. So, oh well. In this case, this length is longer by 1%, but of course that's very difficult to see. So let's look at experiment 1, where we use stimulus displays similar to this. We would present one line segment of a standard length that was either 6 or 9 centimeters, and then we would present a test length that would be physically longer or shorter than the standard, but we would do this sequentially. So we would present these one after the other, not simultaneously. And then the participant's task would be to indicate which length was longer, the first one that you saw or the second. Okay, so let's take a look. So remember, experiment 1 was devoted only to 2-dimensional lengths. As I mentioned, we used 2 different standard lengths of 6 and 9 centimeters. And in this experiment, we had 8 test lengths, 8 test stimuli. 4 of these 8 test stimuli were physically longer than the standard by 1%, 3.5%, 6%, or 8.5%. And then similarly, we had 4 test stimuli that were physically shorter than the standard, again by 1%, 3.5%, 6%, and 8.5%. Okay, and then as you can see, we have data for 3 participants, and of course, one of those was myself. So we're here following the Fechnerian tradition of collecting data for ourselves as participants. And the plots are exactly the same as you saw earlier for object weight discrimination. So we're plotting results for the 8 test stimulus links on the x-axis, and on the y-axis, we're plotting the percentage of those test lines that were judged to be longer than the standard. Remember again that perfect performance for a task like this would look like a step function. And once again, you can see our results certainly do not reflect perfect visual performance. We do make mistakes, but notice for an 8.5% increase in length, right? This participant is performing very well, not perfect, but almost. And likewise, when the test links are 8.5% shorter, this participant, their judgments are almost perfect as well. So we can perform very well if we make the difference in length large enough, which you know, right, from looking at these, right, stimulus pairs yourself. Okay, once again, once we obtain the participant performance for each of the 8 test links, just like before, we find the best fitting psychometric function. And you can see that we had 2 conditions in this experiment, one in which the links to be judged were parallel and had the same orientation. This is what Fechner did, right? In Fechner's case in 1856, he looked at parallel links. However, in the natural world, of course, spatial extents or links are not normally parallel. And so we also included a random orientation condition like you see here, where the 2 links on every trial would be randomly oriented. And notice you get different results depending on whether the links are parallel to each other or randomly oriented. So once again, for each condition, parallel links, random links, right? For each condition and participant, we once again determine difference thresholds, right? So for example, we would go, for example, to get the upper difference threshold, we will go to 75% and go over to a psychometric function and then find out, for example, how much of an increase in length does one need in order to reliably detect that a test length is longer. And similarly, if we want to find the lower difference threshold, we can go to 25% and come over and once again find out how much of a decrease in length do we need in order for a participant to reliably detect that a test length is shorter than the standard. So everything is the same as before. Here are the difference thresholds for each of the 3 participants and difference thresholds in this case for the parallel links, and in this case for the randomly oriented links. And notice how the links are oriented certainly makes a difference. Notice in every case, one needs a larger difference in order to reliably judge randomly oriented links. But nevertheless, performance is good, right? When we visually discriminate 2-dimensional length, we obtain difference thresholds that range from 2.5 to 5.5 or so % of the standard. Certainly, right? Well, one thing, unfortunately for me, notice that my own personal performance is the worst. So I am not as good personally as others when performing this task, but overall, the ability to visually judge two-dimensional length is quite good. However, now let's turn to discriminations of three-dimensional length. That could be quite different. But notice in everyday life, right, the spatial extents that we look at and observe are oriented in three-dimensional space. They're not two-dimensional lengths in a fronto-parallel plane. So what is performance like when we're asked to discriminate three-dimensional lengths? We had two different 3D conditions. In one condition, the two three-dimensional lengths were presented at the same location and depth from the participant. And in the second condition, the two different 3D lengths were located at different locations and depth. And not surprisingly, this task turns out to be more difficult. In this experiment, the three-dimensional, excuse me, in this experiment, the three-dimensional orientation and location of each length and depth was defined by both binocular disparity, right, stereoscopically, and by motion. For example, the kinetic depth effect. So that's how we define the three-dimensional lengths, orientation, and location in space. Everything about the experiment is exactly the same as experiment 1. You can see psychometric functions once again plotted for the same 3 participants. Everything is the same, except now we're just evaluating three-dimensional length discrimination. The standard lengths were the same as before, but notice the difference thresholds were quite different. Notice that in order to reliably judge three-dimensional lengths, performance was much poorer than the performance obtained for two-dimensional lengths. Notice instead of difference thresholds of 2.5 to 5.5% of the standard, we now obtain difference thresholds in the more difficult case, notice, where one has to compare three-dimensional lengths that are located at different positions in depth. Notice we obtain difference thresholds that range from 19 to 24 to 26% of the standard. And so while performance for judging two-dimensional length visually is quite good, notice doing an exactly the same analogous experiment for the visual perception of three-dimensional length, notice our perceptual performance is relatively poor. I mean, this is very rare for a visual task to obtain difference thresholds this high. I mean, this would be the kind of a difference threshold that we ordinarily might have obtained for discriminating differences in taste or smell intensity. So this is not typical for a visual task. Okay, so let's look at experiment 4 briefly, and let's change methods. So instead of the method of constant stimuli, let's look at the method and use Fechner's method of adjustment. So in this case, the displays are not computer generated, but the participants are looking at a physical three-dimensional surface in front of them. So this photograph is taken from an observer or participant's point of view. So the participant is sitting here looking in depth at this three-dimensional surface. And you can see that embedded within this three-dimensional surface are many lights. There are 24 of these lights that, of course, mark different locations in space. And notice that some of these, and so pairs of these lights would indicate distances or spatial extents. Notice that some distances, like this one, occur completely in depth, whereas other distances to be judged do not occur in depth, but are horizontally oriented in a frontoparallel plane. In either case, the participant's task is to adjust the length of a line on the computer monitor until its length matches the distance that you see between any given pair of locations. And on every trial, the computer will illuminate a different distance or length to be judged. So some lengths occur in depth, others occur right horizontally, and then notice that some locations are close to the participant in depth and other locations or distances are located farther away. And this distance, for example, at the back of the surface would be about 1.8 meters. So all of this is located in near visual space where, for example, we have good stereoscopic vision. So this is a direct surface viewed physically, all within 2 meters of the participant and performing an adjustment or matching task. So here is an overhead view of the 24 locations that you just saw. Some distances are oriented horizontally, some occur in depth, some are close to the participant, and then of course some are located farther away. Here are the results concerning precision or reliability. So in this case, we have 6 participants. Of course, I'm one of those. So 6 participants, and these reliability or precision values, what they indicate, we calculated the reliability by calculating the standard deviation of each participant's repeated judgments divided by the mean. So these reliabilities are very good because you can see these standard deviations for all participants and all distances, whether they occur in depth or not in depth. These reliabilities or precision values range from 5.1% of the mean to about 10% of the mean. So these are good amounts of reliability. The participants are being pretty reliable across repeated judgments for the same stimulus. Fechner would refer to this as the variable error. And so the variable errors are very low, indicating good precision and good reliability. However, while our participants were reliable and precise in their judgments of distance, they were reliably wrong. So here are results concerning accuracy. And notice we have results for the 6 participants. And we are plotting results separately for the in-depth intervals with the open symbols and the distances or spatial extents that did not occur in depth, the frontoparallel ones. And then what's being plotted on the y-axis are the adjusted lengths as a proportion of the actual length. So if our participants were accurate in their judgments, all of the data points should be located up here at 1. Well, I think you can see that almost no one was ever accurate under any condition. So at least our participants were more accurate for the frontoparallel or horizontal intervals, At least they were judged more accurately. But look, for example, at the in-depth distances that were judged. The x-axis indicates the distance to each distance. So notice 60 centimeters would be very close to the participant. So these lengths would be very close to the participant, within arm's reach. And whereas these distances here were located 1.5 to 1.8 meters away. And you can see that the distance to the lengths that were judged does matter a lot. So you can see, for example, for this participant, that while his judgments were fairly accurate when the distances to be judged were close to him in depth, notice that as you judge distances that are farther and farther and farther in depth away from the participant, the distances appear to become shorter and shorter and shorter, so that by the time, notice by the time you present an in-depth distance 1.8 meters away, or 1.5 meters away, notice for this participant, they're perceived to be only half as long as they really are. Notice for this participant and also for this one. So it is impressive to me that, notice, if you present a 20 centimeter distance in depth, just 1.5 meters away, many people will perceive that distance to be only 10 centimeters. So that is a rather large constant error in Fechner's terms. So at least our results, and remember that these results were obtained for a real three-dimensional surface located literally within 1 or 2 arm lengths, that even in this circumstance, full Q viewing, using stereoscopic vision, right, and the participants were free to make normal head movements, generating motion parallax in their retinal image, even under these conditions, within 2 meters, within near visual space, notice we have large perceptual distortions. So at least under these conditions, right, we find that the perception of distances and depth may be precise and reliable, but we are precise and reliably wrong, and our perceptions of distances and depth are subject to distortion. So I think, as you have seen, we've certainly found in our own research that Gustav Fechner and Ernst Weber, right, the founders of psychophysics, they made scientific observations about distance and lifted object weight that were essentially correct and completely valid. So we today are extending their work to investigate, for example, how perception is affected by aging. And we also want to extend their work on the perception of distance to how distances are perceived within three-dimensional environments. I think it's admirable that Fechner not only pioneered many aspects of the study of vision and touch, he also began the experimental study of aesthetics. And it's only now, 150 years later, that we're extending Fechner's experimental aesthetics to more complicated objects, in our case recently of snowflakes. And I think that we today have made good progress in extending the psychophysical research began by Weber and Fechner. And I wonder what experimental psychology will be like 160 years from now in 2180. So we will have to wait to find out. I hope that the future of psychophysics will be a good one. So that's it for now, but I'd like to point out that we do study many other things. So we study visual 3D shape discrimination from, using vision. We study tactile 3D shape discrimination. We study object recognition, motion discrimination, material perception and discrimination. You see, we study effects of aging and more. Even for example, notice we also investigate perception of emotion. So all sorts of things. You know, we in my lab are having a good time psychophysically studying many aspects of our environment. And I have been very happy to share Fechner Day with you.